Hello kids. Last class we studied the basics of reflection and reflection of light by plane surfaces. This class we are going to study about reflection of light from spherical surfaces. Okay? Spherical surfaces, I had given you an idea. There are two types of spherical surfaces, convex and concave. And are the images same? Are the images same as the images are formed in plane mirror? Yes or no? Let's see. Let's see. Okay. So see, on the left side, as you can see, this is the plane mirror which have flat surfaces. On the right side, if you observe, these are spherical mirrors. Spherical mirrors are basically curved surfaces. Either they are curved inside or they are curved outside. So these spherical mirrors, as they are curved, obviously they are part of hollow spheres of glass. So if you see this picture, this is an entire sphere. Okay, this is an entire sphere. It's like a piece of glass. And now if this piece of glass, if I just take one piece which I'm highlighting, if I just break off this piece from here and separate it like this. Okay, so I separated it. So now I have this piece with me. I have this piece with me. I have coated this piece. I have coated this curved piece with my silver coating. Okay, this is the silver coating. So this part becomes opaque, right? If we don't put a coating of silver, it would be a transparent glass and light would just go through it, right? Would it be bounced back? No, because for bouncing back, for the phenomena of reflection, we need a opaque surface or an opaque object, okay, which will not allow light to pass through it. So taking this curved surface, what I have done, the other part of this is given a silver coating. So that means that part becomes opaque. So the red part now becomes your reflecting surface. So this is your reflecting surface. Understood? Okay. So this type of mirror, which is curved inside, or you can say the reflecting surface is inside, that type of mirror is called as a concave mirror. Right? Now, again, just the way I have taken this concave surface, if for example, I would have taken the other part, if I would have cut this part of the spherical ball, right? So now I have this part as my curved surface, and I have coated another surface of this spherical ball with silver coating. Okay, I coated this part. I coated silver coating with this part. So this becomes an opaque surface. So this becomes my reflecting surface. Okay. So if you observe the reflecting surface is bulging out. So whenever the reflecting surface bulges out, that type of mirror is called as a convex mirror. Okay, so these are the two types of spherical mirrors that we are going to study. Okay, see now, two types of spherical mirrors. One is concave, another is convex. Over here on the left side, you have a concave mirror. On the right side, you have a convex mirror. So if you see for the concave mirror, this bulge outside part is coated, the black line which you can see is coated with silver lining. So that becomes your opaque surface. So the blue part is your reflecting surface. On the contrary, in case of a convex mirror, the inside part, the concave part is giving a silver coating, and the blue part is your reflecting surface, the bulged part. Okay, see the inside of the mirror, inside of this glass spherical glass is coated and the outside is kept as it is, so that becomes your reflecting part. In case of a concave, it is different. Okay, so this is the difference between what do you mean by a concave mirror and what do you mean by a convex mirror. Okay. Now, before going to image formations by a concave and a convex mirror, there are some important terms which we need to get acquainted with. Okay, because these same terms are again going to be repeated in your lenses part in refraction. Okay, so it's very, very important to just revise these and to understand what all of these means. Okay, now we know that these concave and the spherical, basically spherical mirrors are part of spheres. Now, if it's a part of what is a sphere, sphere is a ball like a surface. We call it a sphere. Now, if it's a sphere always has a center. Obviously, it being a circle type, it will have a center. Without center, can it function? No, it is going to have a center. Now, I'll take an example of this concave mirror now. I am taking out this concave surface from here, and this surface is this one. Okay, gray crescent moon like surface is your concave surface. Now, as this concave surface or the concave spherical mirror is a part of a sphere, it will also have a center. So this becomes your center of curvature. Can you see this? First important term. This is your center of curvature. It is always denoted by C. Center of curvature is the center of the sphere of which the spherical mirror is part of. Again, I will repeat. What is center of curvature? Center of curvature is the center of the sphere of which the spherical mirror is part of. Okay, that is your center of curvature. Next important term what we have is pole. Now, what is pole? Pole is basically the center of the mirror. Okay, so if you see from the starting point to the end point, this is your spherical mirror, right? So this being a spherical mirror, the center of the spherical mirror is called as pole. It is denoted by P. Okay, the third most important thing which we have is principal axis. Now, what is principal axis? Principal axis is a straight line which is passing through center of curvature and pole. Okay, so if you observe this particular line which is going from center of curvature to pole and like passing like this is called as principal axis. Now, all these things are imaginary points which is important for us to study, just to take reference of all of these, just to study how images are formed. All these are imaginary. I mean, yes, it is there, but we cannot see them. Okay, these are imaginary concepts that we take it for our good, to take it for our own understanding. Okay, next we have radius of curvature. Now, what is basically radius of a circle? Radius of a circle is distance between center and any point on the circle, right? So over here also, what is spheres? Spherical mirror. Spherical mirror is a part of a sphere, so sphere will also have a radius, right? Yes or no? Okay, so now the distance between the center and any point on the surface, that is called as your radius of curvature. So distance between C, this is your C, and pole, this is your radius of curvature, denoted by R. Next we have very, very, very important thing that is called as your focus. This is the star of everything. Okay, what is focus? Focus is basically a point. Okay, either it can be in front of the mirror or it is behind the mirror. Depends on which type of mirror you are using. Okay. Focus is a point where all the rays are converged. Okay, Understood? So like for example, I have this concave mirror. Now parallel rays are touching this concave mirror on its reflecting surface. Rays will get reflected back. So they are getting reflected back like this. So if you observe, they get converged at a point. Now this converged point is called as focus, or we call it as principal focus, denoted by capital F. Okay, so this is, so now in case of a convex mirror, now concave mirror is also, there's one more thing to this, concave mirror is a converging type of a mirror. Okay, concave is converging means it will converge the light rays. Okay, it will converge. So if you see parallel rays which were coming, they are getting converged. On the contrary, convex mirror is a diverging mirror. Diverging mirror means it will diverge the light rays. So for example, now this is the convex part. These are the parallel rays which are coming from infinity, and then these will get, this is the point of incidence, they are getting reflected like these. Okay, now if they are reflected, you will say, ma'am, they are not getting converged at any point, so will there be no focus for convex mirror? No, it's not like that. There will be a focus for convex mirror, but what do? We take these diverged light rays behind. We are taking these diverged light rays behind, and the point from where these light rays appear to come from becomes the focus of your convex mirror. Okay, so focus for a concave mirror is the point where all the reflected rays meet, or we can say reflected rays meet at a point. That point is called as focus. And in case of a convex mirror, we can define the focus of a convex mirror as the point from where reflected rays appear to come from. Okay, so reflected rays, in case of a, or you can say reflected or diverged light rays, always appear to come from a point, always appear to come from a point. Reflected rays always appear to come from a point behind the mirror. If you observe, this is the reflecting surface, the blue part. So this point would be behind the mirror. So diverged light rays always appear to come from a point behind the mirror. That point is called as focus, or principal focus of convex mirror. Okay, got the idea? What is the difference between concave and convex mirror? One is a converging, another is a diverging. As far as the principal focus is concerned, in case of a concave mirror, principal focus is a point on the principal axis where all the reflected rays meet or intersect each other. In case of a convex mirror, principal focus is again a point on the principal axis from where the reflected rays appear to come from. Okay, so from, we can just imagine that these reflected rays are emanating or coming from this particular point which is behind the mirror. That is your principal focus. Now as far as focal length, again very important term, because we would be solving many numericals problems with the help of focal length. So focal length is basically the distance between your pole and focus. Okay, can you see this? So this is your focal length. It is always the distance between pole and focus is called as focal length. Radius of curvature, distance between pole and center of curvature is your radius. Distance between pole and focus is called as focal length. Focal length is denoted by small f. Okay, right. Next we have something called as aperture. Now, what is aperture? Aperture is basically called as the diameter of the spherical mirror. So basically, when I say from the top to the end, okay, so this point to this point, this is my aperture. We just name this as M and this as N. So Mn is my aperture. Aperture, we can, if it comes for definition, you can say it's the diameter of the spherical surface is called as aperture. That's it. Okay. Now, principal focus of a concave. If you see, now this object AB, it is at infinity. Okay, so if object AB is at infinity, it is the rays always, and always remember this, whenever the object is at infinity, the rays are always parallel to each other. Okay, whenever you just read a sentence, it says object is at infinity, so always draw parallel light rays which is coming. Rays from infinity are always parallel to each other. So if you can see these blue arrows which are coming, so this is AB is the object which is at infinity. AB being at infinity, it parallel rays are coming out from it. So if parallel rays are coming, if you see this, all these, so here this is the point of incidence, this is the point of incidence, so now all of them are getting converged at one point. This point will be the focus, principal focus of a concave mirror. So that if as the rays are getting converged at one point, okay, they are not going here and there, they are getting converged at one and only one point. That point is called as the principal focus, and hence concave mirror is a converging mirror. Very important question might come. Explain how concave mirror is a converging mirror. So this diagram is very, very important from that point of view. Explain how concave mirror is a converging mirror. You have to draw this diagram, as all the incident rays get reflected at one point in front of the mirror. That point is called as a focus. Hence, this concave mirror is a converging mirror. Similarly, as concave mirror is a converging mirror, let us see what will be the behavior in case of a convex mirror. Again, AB is the object which is at infinity. Light rays parallel to the principal axis are coming and hitting the convex mirror. And if you see, these rays are getting diverged. For example, this is your convex mirror. Let this be the principal axis. These are the light rays, okay, which is hitting the surface of the convex mirror. Now, how are these light rays going to be there? These light rays are going to get diverged. So if you see this, so these are the diverged light rays, the green ones. Okay. So after diverging, how do I define the principal focus then? Because the rays are not meeting. So what we do, we take these rays behind the mirror. Okay. So now this is the point they are meeting. So this point becomes the principal focus. Understood? So if you observe the diagram over here, okay, if you observe, see these light rays are getting diverged and they appear to come from a point which is behind the mirror. So this is your focus. Again, very important diagram. Question, 2-mark question can come. Explain how convex mirror is a diverging mirror, or explain how the principal focus of a convex mirror is defined. So you can draw this diagram and give explanation in 2 to 3 sentences that as the focus is formed behind the mirror, that means we say that rays are considered to come from a point which is behind the mirror. That point we define it as principal focus. Moving ahead. let us define some relationship between focal length and center of curvature. Tell me, what is center of curvature? Radius of curvature. Radius of curvature is basically the distance between center of curvature and pole. Okay, this is the pole. Let it be P. Now this C to A. This is my radius. Okay, so now this radius, and what is F? F is the distance between pole and your focus point. So the relation between radius of curvature and focal length is R is equal to 2F. That means this focus or focal length is basically half of radius curvature. Focal length will lie between the midway. It is the midpoint of your pole and center of curvature. Okay, always remember, because you will be having 1 mark questions based on this relation. So if R, that is the radius, is equal to 2 times the focal length, we can say that the focal length is equal to R by 2. Yes, sometimes the focal length would be given. You have to find out the radius of curvature. If radius of curvature is given, you can find out the focal length. Quite easy. Yes. Now we will proceed towards the image formation of spherical mirrors. So we will be dealing with, again, as we have discussed, 2 types of mirrors: convex mirror, image formations via concave mirror. There are, as far as a concave mirror is concerned, there are 6 types of image formations that we are going to study. And for convex mirror, 2 types of images that we will study. But before studying the image formations, let us study what are the rules that we have to follow while drawing images or while drawing ray diagrams. What are ray diagrams? Ray diagrams are basically what we did till now for a convex mirror, for a concave mirror, wherein you do not take all the rays, you will only take 2 rays or at the max 3 rays, and you will observe where these rays are getting reflected according to these rules, and wherever the reflected rays meet, that point becomes your point of image. Understood? So let us see, there are 4 rules of image formation. Let us see the rules. Rule number 1. Rule number 1 says that if incident ray, we know what is incident ray, we know what is principal axis, we are well acquainted with these terms now. Okay, now if the incident ray is parallel to the principal axis, the reflected ray will go through the focus. Okay, this is your convex mirror, this is the incident ray, this is the pole, this is the focus, this is the center of curvature. Now this is the principal axis. Okay, now if this incident ray is parallel to the principal axis, it has to go through the focus. That's the rule. It has to go through the focus. Okay, now if I take another second ray, the second ray is also parallel, and so if it's parallel, what is the rule? It's going to go through focus. So now wherever these 2 rays are meeting, that point becomes my point of image formation. Understood? So that's why to understand these rules is very important when we have to do image formations. Okay, rule number 1, if the incident ray parallel to the principal axis, reflected ray passes through the focus. Very, very, very important. Okay, second rule. Rule 2 says if a ray of light is passing through center of curvature, it will pass again through center of curvature. That means it will retrace the same path. Retrace the same path. So again, for example, this is your concave mirror. This is center of curvature and this is focus. I have a ray of light which is like passing through the center of curvature like this. I have some object over here and the ray of light is passing through here. Okay, so this is the point of incidence. Now from this point of incidence, this ray of light will get reflected back in the same manner. It will not get deviated or here or there. Okay, it will get reflected back in the same manner. That means it will retrace the same path. That's your rule number 2. If it passes through C, the reflected ray will also pass through C. It will follow the same path. Rule 3. Okay, now this is the vice versa of rule number 1. What was rule 1? If the incident ray is parallel to principal axis, reflected ray will pass through focus. Rule 3, if the incident ray is passing through the focus, it will be parallel to principal axis. This is your concave mirror. This is center of curvature. Let this be focus. So now if my incident ray is passing through focus, my reflected ray will be parallel to principal axis. Understood? At the point of incidence. So every time if you see in these diagrams, at the point of incidence, you can see this gray colored dotted line. That is your normal. Okay. See. Understood? Rule 3, if the incident ray passes through focus, reflected ray has to pass through or has to be parallel to principal axis. Okay. Rule 4. Rule 4 says, okay, I mean, all the 3 first rules are negated. It says that if it is neither parallel to principal axis, nor it is passing through focus, nor it is passing through center of curvature. Okay, it is just hitting the your spherical surface at an angle. Okay, so consider this red incident ray. It is hitting the surface at an angle I, angle of incidence. Each and every point in all these rules in spherical mirrors, laws of reflection are followed. That is, your angle of incidence will be equal to angle of reflection. Okay, so now angle of incidence equal to angle of reflection. So the blue one is your reflected ray. Okay, so blue one becomes your reflected ray. It will be fully in accordance with the laws of reflection. Okay, so the 4th rule says if the incident ray strikes the pole at an angle with principal axis, so that means it is striking the pole at an angle with the principal axis, it makes the same angle with the principal. The reflected ray will also make the same angle with the principal axis. Okay, so that is your 4th law of reflection. Let us revise quick. Rule 1, parallel to principal axis, passing through focus. Rule 2, passing through center of curvature, retracing the same path through center of curvature. Rule 3, passing through focus, parallel to principal axis. Rule 4, if hitting the pole at an angle of incidence, making an angle with the principal axis, reflected ray will also make the same angle with the principal axis. Okay, so these are the 4 rules that you have to keep in your mind so that your image formations with the help of a concave and convex mirror are going to be perfect. It is based only and only these 4 rules, nothing else. It's not a rocket science. You just need to understand and imagine these rules when ray diagrams are to be drawn. Okay, next class, coming episode, we will deal with 6 image formations made by a concave mirror. We will also see image formations made by a convex mirror. We will see the image characteristics made, what is the difference between the image characteristics of these 2 types of mirrors, concave and convex. Okay, stay tuned.